Thought we'd do a video on trying to compare the theoretical values of things with analytical equations, right, and numerical simulations. I don't have a circuit to measure, but I'm going to talk about that as well. And this will be for the quadratic integrate and fire. So the first circuit I'm going to show is a quadratic integrate and fire, where we have a inverting integrator where R2 is 10 times R1 to ensure that the integration constants are the same, because the multiplier we use in our circuits is scaled by 1 divided by 10. Then we have a inverting summer where we bring in an initial condition. Then we have a Schmidt trigger, which when V out goes past V peak, VH will go high, turn this transistor on, and short these two nodes, which is the reset. So when C1 is 0, this will become 0, and then the initial condition, which is summed in the opposite direction, becomes V out. So if I have 1 here, right, when this resets, that -1 times a gain of -1, the 1 times a gain of -1 gives us an output of -1. That's where we get our V reset. And the width of the hysteretic curve, the high switch point, gives us the V peak. Now something else here is a completely ideal circuit where you can actually scale things for time and magnitude scaling and time scaling. I'm not going to go into that too much. Now the integration constant is actually 2500, which matches the best integration constant that I can use in the Anadigm's FPAA. Won't go into it here, but it tends to work pretty well for there. I'll be stepping the input B as a constant from 0.01 to 1 in steps of 0.02. Something else I've done is to make sure that in order for this circuit to work, you actually have to have the reset condition with a delay in it, because there's a feedback loop here, the absolute delay of Vx. Otherwise it won't work. If you make this parameter too small, it's true it gets a little more accurate the smaller it goes, but the simulation time goes up. So if we look at so rather than setting your simulation step here, this absolute delay is actually what's setting your simulation time. So when you run this, all right, you can see that as B increases, the circuit gets spike rate gets faster and faster. All right, now there is some error here, all right, in the spiking rate. But if we look at it, some things are happening a little bit before other things. And so what I do is I actually automatically measure things that when V out crosses V peak divided by 2 for the second and fourth time, which means when it crosses here and here, measure that time. Okay, or that's what it's doing, is measuring the time difference, because the simulation can start off with initial conditions that aren't exactly right. So really it's from here to here. So what you would do here go to the SPICE error log and plot your step to measure data, which I can do here again. And the green SR ideal is from the behavioral source. SR circuit is the actual op-amp circuit, and SRI is from the analytical equation. And you can see that the circuit and the ideal model are matching for almost the whole range, or very close. But the equation derived deviates for B's that are large. Now we can try to see that spiking limit should be a function of B to the 1/2, and it is here. So when I do that, I should get a straight line if it was truly a function of B to the 1/2. And you get a fairly close straight line here, but then you can see that it's not linear in that regime. So there's more to it than that, but there are some issues with that. Now, something else I should point out is that the slew rate, basically how fast it can change, I've bumped up to 100 meg, which might not be realistic. All right, because if it's too slow, what'll happen is, as this is trying to rise because it's the tangent function, right? It's going towards infinity, and the op-amp can't keep up. All right, that's why I changed that one here. So that's great with an gain bandwidth 10 meg, open loop gain 1 meg, current limits and things like that. So that's the universal op-amp. It's almost an ideal op-amp, right? Now then, we thought, well, let's put in the 1630, and which is even a more realistic model. All right, and some strange things happen, is that for small b's, the V out of the circuit is spiking very quickly compared to the ideal. And not only that, the V peak is changing the faster the circuit goes. So the faster the circuit goes, it kind of is overshooting, right? But one would expect to see that behavior. So we look at this as well. And we see the spike rate of the circuit, right, is faster, right? And if I do this on a log scale, you can see that the spike rate is just headed towards some constant value independent of B. And the reason for that is that the 1630 SPICE model has an offset voltage, which is like a little DC input here, which causes it to spike even when B is set to 0. Now, it's a small value, but it will be there, and it'll be there when you build the circuit. Although I have a feeling that the SPICE model open offset is bigger than what it really is. And the model is bigger than what you would actually measure. So anyway, now interestingly enough, the blue line starts to intersect with the other models because it's slowing down, and the reason for that is that since it was overshooting V peak, it wasn't 1 volt, it was much higher. The rise time is just taking longer. And something I needed to point out is that this is a more realistic circuit, and so it doesn't, V peak and VR are not easily programmed. So I ended up changing the ideal model to have V peak as 1.1 and V reset is minus 0.842, because that's what this circuit was doing. And it matches, better when I do it that way. And it was easier to change the ideal model to what was going on in the circuit than try to change the initial condition and things like that. All right. And here, just to re-point it out, is the spiking, the simulation time is just 2.5 times the period it takes to spike. So even though there's errors in this spike rate, okay, I can use it to limit it how fast, how long that this simulation has to go. So each B, as it increases, the spike rate increases, and so therefore I don't have to simulate for as long. I'll just run one here. You can kind of see it. Actually, I'd rather. Okay. So this is the first one where B is small, right? And it'll run for approximately 30 microseconds, right? So there's one spike, 2 spikes, and then it simulates for a little bit longer. But notice how the next simulation stops here. And the simulations keep getting smaller and smaller so that I don't have to simulate for 30 microseconds for everything. So actually this, well, I'm not going to take a video of LT Spice running, but so that what's going on is that I'm trying to find, here is, I have an ideal model, then I have an analytical model, which is we've seen from lab manuals and things like that and derivations, right? And then we have a circuit with the using the universal op-amp model with a slew rate of 100 meg, right? And then we have another QIF where we're using an even more realistic op-amp model. Now then the next step would be to do this in a field programmable analog array and just step B and measure it in Scopy and measure the period of the output, right? And so that you would have a chart of, what is the spike rate at various B values for the ideal model. For the op-amp model, that's the most realistic. For the op-amp model, that's the least realistic, and then measured in the field programmable analog array. And then, if you had it, the circuit that you actually built, right? And so then you could compare everything, right? But what's important is that the integration constant has to be the same for all these circuits. V peak and VR would have to be the same for all these circuits. That way you can really get at what the deviations from ideal, which then you might fix or you might ignore. Something too is that if you are let's take this one here, right? You've set B to some value. This peak will bounce around in a real circuit because it's crossing a threshold and there's noise in the circuit, and sometimes it'll cross the threshold sooner, cross it later, and so it will bounce around. And so when you measure the period of spiking, yeah, there'll be a standard deviation to that, right? And then what would be good to analyze is, I have a spiking rate here, but how much does the spiking rate jump around, right? So if when you've made it, it's bouncing around so that there's no difference between these two lines, it tells you that it's not worth pursuing anymore. But I have a feeling that the ideal equation is not correct for higher input. Okay, even though it seems to be that's the derivation, there's something it just really seems to be missing. I don't think it's although one thing to investigate is, right, in SPICE, right, what is the tolerance of everything? There's a lot of numerical things in here that would affect the integration. Then there's also even different forms of integration. If you take a numerical methods course, you'd find out, which I think EE 104, even though it's Python, it teaches you a lot of numerical methods as well. Anyway, that's kind of the big picture for if you're doing research in this area.